Let's talk about training. You know from the previous video that the model consists of a parameter configuration and a formula how the input and the parameters are to be combined to compute the output, the architecture. In this video, I want to give you an intuition of how the training actually works. Let's say you have a very simple model with only one parameter p, and the model architecture, which combines the p by multiplying it with the input I to get a head O, the prediction. You also know the desired output O. Intuitively, during training, we look at each data sample and check if the prediction and the desired output are very different or if they are very similar. If they are similar, this means the model has made a good prediction. If they are different, the model has failed. Whenever the model has failed, we want to change the parameters such that afterwards the head O and the O are more similar for this sample. Mathematically, this can be written as minimizing the difference between the prediction and the true output with respect to the parameters. This difference is also often called loss function. Think of this distance function as a simple polynomial, where its optima can be found exactly how you might remember from middle or high school math, by setting the first derivative to 0. Since you are currently only looking at one specific training sample, you might not want to change the parameters to completely different values. Instead, you typically look at batches of samples and only update parameters for whole batches. And second, update the parameter only a fraction into the direction of the optima. Together, this is called stochastic gradient descent. The goal of this process is to yield a model that is able to produce sensible output for input that it has not seen during training. This property is called generalization. It is important that you sensibly choose the size of your batches and the learning rate with which you update your parameter, that you compare the model prediction quality on training samples with the one on the evaluation set. If the performance on the training data is significantly stronger, overfitting has occurred. Here you might refer to regularizing your model. In SPACY, you can expect that the configuration of a model has sensible defaults, and then when unexpected things happen, such as weak model performance or overfitting, this can typically be mitigated by external means. For example, rephrasing your machine learning problem, preprocessing your data differently, acquiring more training or evaluation data, cleaning misleading samples from your training data, and so on. The terms that we used in this video were input, parameters, prediction, desired output, optimization, loss function, batches, learning rate, stochastic gradient descent, generalization, and overfitting.